Hello, Lower Six. We're starting a new topic today, which is electric circuits. This is a topic, of course, that you would have covered in quite a bit of detail at GCSE. So the beginning of the topic really is a bit of a reminder just to get you up to speed with things that really you should have learnt from GCSE. Sometimes at GCSE, concepts like potential difference are not 100% clear. It's important at A level that we do make sure that they are clear, particularly understanding the difference between potential difference and current is really key to understanding electric circuits. So, the work we've got for you this week, there's going to be, like as before, there's going to be some notes for you to write down. We do need you to learn the circuit symbols. So one of the first things that I'm going to get you to do in the notes is just copy down a list of circuit symbols that you need to learn. Obviously, when you're drawing electric circuits, it's easier to use symbols than try to draw a circuit as it actually appears. Okay, so quick reminder then of a basic electric circuit and what's happening, and then we'll talk about what potential difference and current and resistance are and how we measure them. So let's begin. We've got a basic circuit here, no different from what you would have seen at GCSE. In fact, you probably started playing with circuits like this all the way back in primary school, some of you. What we've got is a power supply. Now, of course, you could have a battery instead of a power supply. No reason why you can have a battery, but we've got a DC power supply. I managed to grab one of the decent ones from school. We've got a switch, we've got a light bulb, and we've got an ammeter, and they're all connected by a conducting wire. So that's the most basic electric circuit imaginable. And what's happening with an electric circuit? Well, the first of all, the circuit is complete when we press the switch, and when it's complete, the electrons inside the wire is a conductor, which means it contains free electrons, will get shunted along the wire by being basically pushed away by the negative end of the power supply. Now, if you look at the power supply, that end is negative, that end is positive. These are the terminals of the power supply. Same idea on a battery. Now, if it's a battery, a chemical reaction inside the battery keeps one end positively charged and one end negatively charged. In this case, you've got a transformer inside here, and it's connected to the mains. However, this end here is negatively charged. This end here is positively charged. When we connect it to a complete circuit, what happens is the electrons inside the conductor will get shunted along. They'll move from the negative around the circuit and back to the positive. Of course, negative charges repel negative and they're attracted to positive. And there'll be a continuous stream of electrons passing around the circuit as long as the circuit is complete. Okay, as soon as the circuit is broken, that flow of electrons will stop at all points within the circuit. So that's the idea that you're probably familiar with from GCSE and beyond. You should really understand how an electric circuit works. The electrons get shunted along the wire by being pushed and pulled by the positive and negative terminals. When you draw a circuit diagram, by the way, you often put an arrow on the wire to show the direction of the current. By convention, and this is kind of important, you always draw the current as going from positive to negative. So that's actually in the opposite direction to where the electrons are moving. So the electrons, remember, are moving this way around the circuit because that's the negative terminal, that's the positive terminal. If you were to draw this as a circuit diagram, you would have the arrow for the current going that way around, going from positive to negative. There's a little bit of history behind that. When electric circuits were first devised and first being built, it wasn't clear what was actually flowing around the wires. They understood that it was electric charge that was flowing around, but they didn't know whether it was positive or negative charge. The electron had not been discovered at that point. So I guess they took a guess and they said positive charge is flowing. And so by convention, it became established that a current is a flow of positive charge. So if you imagine there was a positive charge in this wire, that would be going round in that direction. Now in some materials, for instance in an ionic liquid, you will get positive charges flowing. You'll actually get positive and negative flowing in opposite directions in an ionic liquid if you put a potential difference across it. But in the case of a conducting wire, you'll just have negative electrons that are flowing, in which case they move in the opposite direction to the conventional current. But don't worry too much about that. Just remember that the convention is, if you're drawing current in a circuit, you draw it from positive to negative, not the other way around. And really, it doesn't actually matter. Okay, so that's the basics of a circuit and how a circuit works. So obviously the components we've got in here, we've got a switch, we've got a light bulb. Light bulb's got a filament in. When the current goes through the filament gets hot and it glows. And we've also got an ammeter. The job of the ammeter is to measure current in amps. So we're going to talk about what the definition is of current and potential difference. Well, first of all, current is probably the easiest one to understand for most people. It's a measurement of the flow of electricity or the flow of charge. It's how much charge passes a point on the wire in a second. Now, charge is measured in coulombs. Okay, 1 coulomb is an amount of charge. It's equivalent to 6.25 million electrons. So 6.25 million electrons flow past a point in the wire every second. That's a current of 1 amp that's flowing. So 1 amp really is the same thing as 1 coulomb per second. Or 1 coulomb is 1 amp second, if you want to think of it the other way around. So that's what current is. It's the amount of charge that's flowing past a point every second. So obviously if I switch this on, you can hopefully see on there it should be reading a current about 1.71 amps. So that's the first important thing. Now this device is an ammeter for measuring current. You always place it in series with the component that you're measuring the current through, because the current has to go through the ammeter. So it has to be part of the main circuit. Okay, so the ammeter is always in the circuit. It's part of the circuit. The current goes through the ammeter. They will test you on this quite extensively. How do you set up a circuit to measure current and potential difference? And if you get it the wrong way around, where the ammeter and the voltmeter go, you can really mess up. So just remember, ammeter goes in the circuit or in series with the circuit, which means in a daisy chain with the rest of the circuit. The current has to go through the ammeter. As far as the ammeter itself is concerned, if it was a perfect ammeter, now no ammeter is perfect, but if it was a perfect ammeter, it would actually have no resistance. So actually it has no effect on the circuit that you're measuring. Its resistance in theory is 0, which means it's just like another piece of wire. So you can almost pretend the ammeter isn't there, which is exactly what you would expect, because the instrument you're using to make a reading from the circuit, you don't want that to actually change the circuit at all. So the ammeter essentially is not there. It's you can think of it as just being a wire there, that it's got no resistance. It just measures how many coulombs pass through the wire every second. So that's the relationship between charge and current, okay? And there is obviously a formula for that as well. If you want to know how much charge passes this point in time t, well, if you multiply the current in amps by the time in seconds, you get the charge in coulombs. So the formula is Q equals I times T. Q is the symbol for charge, I is the symbol for current. Q is measured in coulombs, which is symbol C. I is measured in amps, which is symbol A. Try not to get confused the symbols for the quantity and the unit, okay? So obviously charge, quantity, Q, unit, C. Okay, C for coulombs. Current, quantity symbol is I, unit symbol is A. Okay, every measurement has both a quantity and a unit, and they each have a different symbol. So charge, it's Q and C. Current, it's I and A. Sometimes people get these mixed up. So that's what current is. Hopefully you all understand that and you all appreciate that. Again, it's nothing that you wouldn't have learned at GCSE, although some people don't learn it particularly well at GCSE. So the other thing that we want to measure is what's actually causing the current to go round the circuit. Now you can see if I turn this on, let's come off here. Sorry, it's just warming up. There we go. So you can see if I turn this on, I can actually change the current that's going through the ammeter. I can change it by turning the power supply up and down. Okay, so you can see that by the bulb getting brighter and dimmer, and also by the ammeter getting higher and lower. But what's actually causing the current to change in the circuit? Okay, what is it I'm doing to the power supply that's changing the current in the circuit? Well, what I'm changing is the potential difference across the components in the circuit. Now, potential difference is sometimes called voltage as well, so try not to get too confused by that. It can be called voltage. It's measured in units called volts. You can think of potential difference a bit like the push that's required to push a current around a circuit. In terms of units, it's measured in volts, and 1 volt means that it takes 1 joule to get 1 coulomb of charge through a component. So if I was to measure the potential difference across this light bulb, okay, I'll show you how that's done in a minute, but if I was to measure the potential difference across the light bulb, if that's 1 volt from one side of the light bulb to the other side of the light bulb, it means that every coulomb of charge which passes through the light bulb will transfer 1 joule of energy. What does it transfer it to? Well, it transfers it obviously into light, but also heat as well. Okay. What's it transferring it from? Well, it's transferring it from electrical potential energy. Okay, so it's transferring it from electrical energy into heat and light. So the potential difference across a component is how much energy is transferred by 1 coulomb of charge passing through. So obviously, the higher the potential difference, the more energy is required to push the current through the component. And if you turn up the potential difference, now what's supplying the potential difference is obviously the power supply. If you turn up the potential difference, you'll get more current through the component. Now, the potential difference on its own doesn't determine the current, because I could put in a different light bulb here and I'd read a different current. It also depends on the resistance of the component as well. So a higher resistance light bulb will take more potential difference to get the same amount of current going through. So we'll talk a little bit about resistance in a minute after I show you how to measure potential difference. But resistance is basically a measure of how difficult it is to push current through a component. So here we've got a light bulb. It's switched on at the moment. We've got a current that we're measuring through it now at the moment. I'll just read the current. 1.26 amps. So that's how many coulombs per second passing through that light bulb. If I want to measure the potential difference across the light bulb, what I need is a voltmeter. Okay, and with a voltmeter, I do connect it in a different way from the ammeter, and this is really important. With a voltmeter, you're measuring the potential difference across a component, not through a component, and so you need to put it in parallel with the component. So I'm going to take the positive side of the voltmeter, I'm going to connect it to the positive side of the light bulb, which is this side, and then the negative side of the voltmeter and connect it to the negative side of the light bulb, which is this side. So I've actually put the voltmeter across the light bulb, not in series, I put it in parallel. And you can see, I don't know if you can see the reading on there, 6.63 volts. So we're taking a couple of measurements there that are quite interesting. We're saying that 1.26 coulombs per second pass through here, and we're saying that each coulomb that passes through converts 6.63 joules of energy into heat and light. So two useful measurements there. If we were to multiply these two measurements together, we've got 1.26 coulombs per second and then 6.63 joules per coulomb. What we'd get is the number of joules being converted per second into heat and light. In other words, we get the power output of the light bulb. So that would just be current times voltage. Okay, so that's what we mean by potential difference. Really important that you understand what potential difference is and you understand what current is. There will be notes on this. Finally, the last thing, I did mention resistance. What do we mean by resistance? Okay, so resistance is a quantity that we measure to express how difficult it is to push current through a particular component. Now, as I said, if you've got a high resistance component, it'll take more potential difference to push 1 amp through it than a low resistance component. So I'm just going to show you, I'm going to take the light bulb away for a minute. So I'm going to disconnect the light bulb. And I'm just going to show you this. That is a fixed resistor, okay. On the other side, the component is mounted in a cooling unit, okay. But that is a fixed resistor. A fixed resistor has a fixed resistance, a little bit different from a light bulb. We'll talk about that in the next lesson. But a fixed resistance. Now this one, you can see on the label there, it says 10 ohms. Now what that means is it takes 10 volts to push 1 amp of current through. Now, because this is a fixed resistor, it's got a constant resistance, which means that the potential difference in current are proportional. So it would take 20 volts to push 2 amps through. So I don't know if that makes sense to you, okay? But the resistance is the ratio of potential difference divided by current. Okay, so if I wanted to measure the resistance of this, well, we know what the answer is going to be. It's going to be 10 ohms. But let's supposing we didn't know what the resistance of this particular component is. What we do is I'll just take the light bulb away. We'll connect it in exactly the same way as we did before with the voltmeter and the ammeter. So the ammeter's in series, the voltmeter is in parallel. I'm going to switch this switch on. Okay. Now, unlike the light bulb, we can't see anything exciting happening because it's only converting energy into heat. It is getting warm, but there's no light coming off. But nonetheless, same thing's happening. We should have a current and we should have a voltage. So what have we got? So the current is 0.68 amps. Okay. And the voltage is 6.78 volts. So obviously, if we do the ratio of voltage divided by current, 6.78 divided by 0.68 is very, very close to being 10. So the ratio of potential difference divided by current gives you the resistance. So R equals V divided by I is another formula that you need to learn. That's the definition of resistance. So overall, then, 3 formulas you have to learn today, okay, as part of your notes, and there'll be some questions on this in the homework. There's definition of current, which is Q equals I times T, okay, or I equals Q divided by T, depending on how you want to write it. Definition of potential difference, which is energy transferred or work done, W equals Q, charge times V, which is potential difference. And then the definition of resistance, which is the ratio R equals V divided by I. 3 triangular formulas, very simple to manipulate and use and learn. And that's all we need to learn in the next couple of days. Okay, so I'm going to set you some homework for the end of Friday. We are going to, on Show My Homework, I'm also going to put a link to a Zoom lesson I'd like us to have whoever can make it, have a Zoom lesson at the normal lesson time on Friday, which would be 11:40, where I'm going to have a look through your test results for the Mechanics 2 test. Okay, I hope that's all fairly clear. Do email me, of course, if you've got any questions at all. Thank you very much.